So our next speaker is Mahendra Mariadassou from Greece, and Explicit Labs,
Okay. Well, first of all, I would like the organizers for giving me the opportunity to give this talk. This is a PhD work I'm doing with my advisor, Avner Baren, and I'm going to talk about some bonds for the stability of maximum likelihood trees. So first, what's the stability issue in phylogeny? You might be more knowledgeable than me in this, but when you infer topology, the inferred topology might not be the true topology. And this causes problem when you want to draw some conclusions for the topology. One of the most basic questions is how confident are you in the clad? And one of the causes of variability in the inferred topology is data sampling. That is, you only have a finite number of sites, and so you are not able to infer correctly the correct topology. And in my talk, I'm going to focus on maximum likelihood methods and their statistical properties. So I'm sorry, but I need to introduce some notations. I hope they're not too horrible, but you might be familiar with most of them. The data matrix is just the alignment. So you have it's a matrix of size S, the number of spaces, times n, the number of sites in your sequences, and the nucleotide, the coordinate x, y, x, I, G is just the nucleotide G in the species E value, which since it's nucleotide takes value in ACGT. The basic statistical unit I'm interested in is a column of that matrix, which is the nucleotide pattern at site E. It's a vector of size S, which is the number of species. And for example, if I have 6 species, the nucleotide pattern can be AAA, TTT, or I could have AT, 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 and I think you get the idea. And what I call a phylogenetic model is the combination of both a tree topology, that is a branching pattern with the branch lengths, and the evolution model, a substitution model with the associated parameters. So it doesn't matter exactly what evolution model you consider. The thing which is really important about this phylogenetic model is that given a nucleotide pattern and given a phylogenetic model, I can compute the likelihood of my pattern under my model. So I need both the topology and the evolution model. Just like in every likelihood framework, we suppose that the basic statistical unit, so here the columns of my matrix, are IID, independent and identically distributed with the same distribution Q. And we're also interested in the empirical distributions of the nucleotide, which you get from your data set. And one thing which is quite important is that we're interested in the real distribution of the patterns, which has a priori no reason to be given by the combination of a topology and a substitution model. It can be quite different. One point of interest is that the support of the real distributions of the pattern can be quite smaller than the number of possible patterns. If I take an example, if you have 20 species, the number of possible nucleotide patterns is 4 to the 20, which is quite a huge number, but there is no reason that all these 4 to the 20 patterns are possible in fact. Given the Markovian time reversible model, usually they are, but there is no reason that they are admissible under the true distribution. So we're interested in the support of the true distribution, which is a subset of all the nucleotide patterns, and which is and as a subset, as the number of elements, which is smaller than 4 to the S. Given this true distribution, you can compute the true likelihood of a model, which is just the mean likelihood of a nucleotide pattern under model T, under the true distribution of patterns, and the empirical version of this likelihood, which is exactly the same thing, except instead of taking the true distribution of patterns, you take the empirical distribution of patterns. What I know by probability of X under T is the probability of observing pattern T under model T, of observing pattern X under model T. So one important thing here is that when you're doing some maximum likelihood, when you're doing likelihood stuff in phylogeny, you would like to work with the true likelihood of a model, but you would never have access to this true likelihood because it would require knowing the true distribution of the nucleotide patterns, or equivalently, having having a sequence of infinite length, you only have access to the empirical likelihood. So I'm interested in the distance between the empirical and the true likelihood score of a model. So we can see the likelihood score as a scalar product. That's what I'm explaining. Q is the pattern distributions. Since there are only finitely many distribution patterns, I can replace this distribution by its parameter vector. That is a vector of size the number of possible patterns, where theta x is just the probability under the true distribution of observing the pattern, of observing the nucleotide pattern x and the empirical version of the same quantity, which helps me to define two vectors of size the cardinal of ns, which contain exactly the same information as the two original distributions q and qn. And then you can note that we're only interested in the patterns that have a strictly positive probability of apparition under the true distribution. And we're interested, in fact, in their log likelihood under model T. So since there are only as many, we can also put them in a vector, and then the log likelihood of model T can be expressed as the scalar product of the vector theta, which encodes the information for the true pattern distribution, and the vector log pt, which encodes the information for the phylogenetic model at which interests you. And you can have you have the same quantity, but defined in the empirical way. And it's quite easy to see then that the difference between the true likelihood of model and its empirical version is just the difference between theta minus theta n scalar the vector log pt. So to control the difference between these two log likelihoods, I need to control this vector theta minus theta n, which is the difference between the true and empirical pattern distributions. And large deviation theories tells us that the probability of this vector being big, let's say larger than a given epsilon, decreases exponentially towards 0. And we are interested at exactly what rate does this difference decreases towards 0. And using some Michaud concentration tool, we obtain that the log probability of this event decreases at this rate. I don't want to enter into the details. I just, because this is not really the quantity we're interested in, we would rather have some results on the difference between the likelihood scores. Taking advantage of the relation between the likelihood scores and the pattern distribution vectors, we can obtain a result which says that the log probability of the difference between the likelihood score between the true and the empirical likelihood score of a model being too big decreases exponentially, but this time you have a constant here, basically 2ns, which is twice the number of possible patterns under the true distribution. And here you have something which is minus epsilon tilde. It looks exactly like the previous formula, except that here the epsilon tilde is much smaller. So to detect the difference of epsilon, you have to detect the difference of epsilon before the decreasing rate was going down with something like epsilon to the square. And here the decreasing rate is epsilon divided by something which can be quite big, because it's epsilon divided by the number of possible patterns and the log likelihood of the less likely nucleotide patterns in all nucleotide patterns. So the nice thing about this is that for a given confidence level, for example, if you want your probability here to be small, you can compute the number of nucleotides you need to achieve this small probability. Another thing is that for the bond is very sharp. This bond includes this number, so the number of total possible patterns in here and in here. So as the number of possible patterns is low, you have a bond that is sharper. So we need to have it incites us to have an accurate estimation of the number of possible patterns. And for simple models, patterns can be merged because we are interested in nucleotide patterns only as far as they provide different log likelihood, only as far as they have different log likelihoods under model T. So this is one thing, but what we're really interested in is the ranking of the likelihood scores of different models. Because when you do some when you use some maximum likelihood method, usually you compare model, you give them a likelihood score, and you pick the score with the highest likelihood, and you pick the model with the highest likelihood score. And here, the bad thing about not having the likelihood scores, but only empirical likelihood scores, is that inversion events can happen. Consider you have two models, T and T prime, and the likelihood scores give a certain ranking. For example, T has a lower score than T prime. You would like to retrieve T prime, but it can happen just by chance that considering your data set, T prime has a lower score than T, which is something you don't want. And the question is, how often does such an event happen? And you believe that the probability of such an event decreases when the available information increases, and in what way? So using exactly the same tools as before, we obtain this result, which says that if you have a model T that is better than a model T prime, in the sense that it has a higher likelihood score than the other one, then the probability that the lower score model is better than the other one for your data set is such that satisfies this inequality. And here, the exponential decreasing rate is the difference between the true likelihood scores of the two models divided by something which is like the quantities before. And this is a result we can expect because the inversion probability decreases with the difference of the likelihood scores. If you have two models that have widely different likelihood scores, it will be easier to tell that one is better than the other. But if the likelihood scores are very close, you will have many mistakes when trying to tell which one has the highest score. And once again, you can use some tricks to decrease the number of possible patterns because you're only interested in patterns which have which provides different likelihood for the two models. So those patterns which provides the same likelihood for the two models at hand, you can discard. We wanted to compare the method with Bootstrap. The aim of Bootstrap is to evaluate the probability of the inferred phylogeny not being the true one. And one of the problems of Bootstrap, at least non-parametric Bootstrap, when you resample from the data, is that the only variability that you observed, that the only variability that you take into account is the variability that's present in the data set. And we also found some significance threshold, usually 66% and 95%, which are not justified. For example, it's not absurd to think that the significance threshold should depend on the number of spaces and the number of sites at hand. And the last limitation of Bootstrap is not really a limitation with the increasing power of computers. And some aspects of the bounds we obtain is that they account for more variability than just the one observed in the data, because basically we want to take all the nucleotide patterns that are admissible under the true distribution of patterns. They account for the number of species and the number of nucleotides when we compute a confidence level. And for a given set of admissible nucleotide patterns, if we want to achieve a given probability of making a mistake, we know exactly how many sites we need. And one of the tricks we use is that instead of focusing on topologies, we focus on the likelihood score associated to a topology. So one of the drawbacks is that if two models have exactly the same likelihood scores, we won't be able to tell them apart. This is a PhD work, so there's a lot of things still to do. I depend a lot on the number of patterns that are possible under the true distribution. This is unknown because we only sample from the true distribution of pattern. So it's highly possible that we will miss some nucleotide patterns when we get the sample. It's very important to have some bounds on the true number of patterns, considering the observed number of nucleotide patterns. We would for the time being, we can only do stuff when the models have been chosen a priori. It would be more useful to do some things with models that have been chosen with respect to the data. And we would like to compare method bootstrap on data. And we would also like to consider process bounds instead of pointwise bounds. That is, how does the probability changes when I add some information? That is, when I increase the length of my sequence. And I can also add anything else I can think about and have time to do. My time is done, so I'll stop here. Thank you for your attention.
Questions?
So if you, let's say that the model is very simple and maybe the transitions are rational or whatever, then you could maybe produce exactly the true distribution, and then inferring it in principle is easy. But usually it's not the case. And also, for real things, you could get more than one maximum of the likelihoods. I'm wondering if your method could be used to get some sort of ball of confidence around, around the true distribution in which you could guarantee that you will have a unique maximum which is close to the original. Can you do anything like that?
I've not thought about that, so I'm not able to answer the question, but that might be something nice to work on. Yes.
So, two things. First, I don't exactly see how asymptotically two patterns get the same distribution, the same probability under two different models, and how asymptotically one pattern gets zero probability under any model. So this is the first question.
Okay.
And then, you spoke about two models here.
Yeah.
Do you distinguish, sometimes it's even enough to distinguish between two models that are topologically different? Do you make any distinction between two models that are topologically different, or models that same topology but different branch lengths?
A model is something in which you impose a lot of things: the topology, the branch length, and the substitution model. So when you talk about, one way to compare two models would be to fix the models. That is, you fix the topology and then you make the branch length vary. This would lead to different pattern distributions, which might be close or distant to the true distribution of patterns. And when you do this kind of stuff, you want to retrieve the pattern distribution induced by your model, which is close to the true pattern distribution. So varying only the branch length might be enough to distinguish one model to another. And you expect that when you vary the topology, then the pattern distribution associated to one model is even more different than when you vary just the branch length. And for the first question, the thing is, there are two distributions that we're interested in: the true distribution of nucleotide patterns and the distribution of nucleotide patterns which is associated to a model. Usually, the distribution associated to a pattern gives a probability, a strictly positive probability to any distribution patterns. But this might not be the case for the true distributions. There is no reason that when you consider 20 species, the 4 to 20 distribution patterns will have a strictly positive probability of operation. And this is even the case if you consider, for example, maybe 100 is not enough, but if you consider 200 species, there are 4 to the 200 possible distribution patterns, and this might be more than the length of the biggest genome.
You are talking about expected number of the pattern. You want it to be bigger than one, correct?
Yeah, I'd like it to be bigger than one. Yes.
Could I ask what exactly is N sub S? Could you explain again what N sub S is and how it's related to the observation model, right? It's accurately estimate script N sub S, right? What is N sub S?
Script N sub S is the support of the true distribution of patterns. That is, it's the
not simply a set of all patterns.
It's not simply the set of all patterns. It's the subset of all patterns that you expect to observe. To come back on the question of the previous speaker, that would be the set of patterns we've expected values greater than 1 or greater than some strictly positive values.